example. Okay, so let me draw that. So this is an application. Okay, so an example of projectile motion using the equation. So the situation is this. Maybe I could use here my drawing, right? So you have this mountain. It's a high mountain. Okay. And on this side of the mountain, you have a guy with a mortar. So a mortar is here. And this guy is going to throw a projectile over the mountain in order to hit something on the other side of the mountain. Right? So if you look at this on a profile, this is what you have. So you have the mortar pointing there. Okay. And then we have the mountain around here, right? So then the ammunition is going to go there and hit that point P on the other side of the mountain. So you're going to use this mortar to throw this projectile. It's going to go over the mountain and hit this point P. So let's assume that's the point P that we are talking about here. That's the point P on the other side of the mountain. And the projectile is going to do that parabola, is going to hit that point P. So, why we are interested in this point P? Because there is a guy, he's a kind of a spy. So this guy is laying down the ground here, and he has this binocular, some kind of apparatus that he is using, and he can see a tank that is around here. So there is a tank, right? There's a tank, and that tank is moving towards the point P, and I put that velocity 30 kilometers per hour. So the velocity of the tank 30.0 kilometers per hour. So the tank is going towards this point P. And just to be easy, but look, no need for that, okay? But just to be easy, I put that the tank is going to be exactly perpendicular to the line that the mortar, to the plane that the projectile of the mortar is going to get to point P. But eventually that's not necessary, okay? You could have some angle. You could have this tank going eventually in a little bit different direction. We could work with the components of the velocities and solve this the same way, okay? But just to be easy, let's assume that the tank, well, where is the cannon of the tank? Is here, okay? So the tank is going 30 kilometers per hour towards P, and this guy is going to try to hit that tank when he hits the point P, okay? And this guy here on the mountain, the spy, right? He is looking at the tank, and he has this kind of a communication with the guy here on the mortar, okay? So they are communicating with each other, and this guy here says, I can see a tank moving 30 kilometers per hour. So that's possible. We have some kinds of devices that can do that. What's the speed that the object is moving, okay? And so he's moving 30 kilometers per hour, and he's going to be on that point P that is in your line for your mortar, okay? And then what this guy here needs to do? Well, he needs to know something in order to solve this, right? So for the mortar, he knows something about this gun. The first thing that he knows is that the velocity of the mortar, of the projectile of the mortar, is, for that kind of ammunition that is enough to get that tank, is 162 meters per second. So that's the velocity, the V initial, that the ammunition is gonna be, so that's the V initial of the ammunition of the mortar is being launched, 162 meters per second, right? Obviously, one thing that he's gonna have to know here is the angle theta, right? But let's see. Second thing that he knows the range. In some way, I bet to that guy, or they knew that using a map, what is the distance between the position of the mortar and the point P? Which is the range, right? The delta X max that we're going to use for that mortar. And let's assume that is 1,800 meters away. So the point B is 1,800 meters away, is a little bit more than a mile, right? So it's a mile and 200 yards. So that's the distance between the position of the mortar and the point P where the tank is going to be. Okay, where the tank is going to be. Other thing that he knows about this mortar is that the angle that the mortar can fire has a limit. Okay, and I got this from the encyclopedia. Okay, so this can throw an ammunition between 45 and 85 degrees. And this kind of ammunition, to be enough to destroy that tank, is 162 meters per second, right? So what I'm saying here that this kind of mortar is just ballistic, is what we call ballistic. When an object is being launched, and then the only force that acts on the object is gravity and eventually air friction, but we are not going to consider air friction here. Let's assume that it's close enough to not consider air friction, right? So we say that the motion, the trajectory of this ammunition is ballistic because it just goes with gravity, right? And some air friction to get there. So it's ballistic motion because maybe this mortar is a little bit old because today we have ammunition for mortar guided ammunition by GPS or by other sophisticated kinds of device. But let's assume that this mortar is a little bit old and that's going to be ballistic. And then comes the question, right? What this guy here needs to do is to think about some angle theta to get to the point P, right? And because the projectile is going to take some time to get there, there is a time of flight involved here, right? So once that this guy fired the ammunition, it's going to take some time for the ammunition to get to the point P. Meanwhile, the tank is moving, right? So the ammunition needs to be in P exactly the same time that the tank is going to be in P, right? So this guy here, look for this arm. This is a very smart guy. He has a calculator. Can you see the calculator in his hand? And he's going to do the calculations and see first if it is possible to get P, if there is an angle on this range to get P. And once that, okay, there is such an angle, he's going to say, how much is the time of flight? Okay, I got the time of flight. So what distance the tank needs to be moving 30 kilometers per hour in such a way that the time that the ammunition is going to take to get to P is exactly the same time that the tank is going to take to get there moving 30 kilometers per hour. So there is a distance here that he's going to ask that guy that is there watching, right? So there is the tank. So he is going to make contact with that guy, is going to say, there is this distance. When the tank gets there, you immediately tell me that I'm going to fire. Because then I know that it's going to take some time, the tank is going to take some time, and it's going to get there exactly with the tank, right? So here comes the question. Knowing this, knowing G, right? We're going to see G minus 9.8 meters per second square, right? That's G. We're going to assume that this is free fall. There is no air friction, right? So then there comes the question. Where is this point? If that shot is possible, right? Inside the range of the mortar, where is this point that the tank needs to be? Because then this guy here is going to tell to this other guy, the guy A, is going to tell to the guy B, look, when the guy got to this distance, you talk to me, and I'm going to fire the mortar. And then I'm going to take this tank down. Okay? So let's see how to solve this, right? So the first thing that you're going to do, right, is to eventually you could think that there is more than one answer for this, right? Right? Because eventually, if the tank is a little bit further, you could think that you could fire this mortar higher angle. The time of flight increases, you still can get the tank in P at the same time than the ammunition, right? So it does look that this is kind of a problem that has only one solution, okay? Eventually, it has more than one solution, right? But I'm gonna do this. I'm gonna start from the range, calculate the time of flight, thinking about this velocity, get the angle, see if the angle is in this range. If it is in that range, I'm going to calculate the distance. Okay, so I'm going to work a little bit backwards, right? But eventually there are other solutions for this problem, not just a single solution, right? So let's see first about the angle. What's the angle theta that he needs to fire the mortar to get in P? Once that we know the range here, so this is 1,800 meters far away, right? So what's the angle theta to get there? So we just use the equation for the range, delta x maximum, the range. It's going to be V initial square over G, right? Sine of 2 theta. So that's the equation for the range. How much the delta x max? 1,800 meters. How much the V initial? 162 meters per second, 162 square, divided by 9.8, G, sine of 2 theta. So solving this, we can have the sine of 2 theta. So I'm going to take the 9.8 multiply, divided by 162 square, right? So then we have that the sine of 2 theta is going to be the sine of 2 theta 0.67215, right? So the sine of 2 theta 0.67215. If we call this alpha, we can use our calculator and do the sine minus 1 this and get in alpha. Okay, we are going to call this 2 theta alpha and then do the sine minus 1 and I'm going to have the angle alpha. Doing that, sine minus 1 of this, we get for alpha 21.1 degrees. Okay, so I got 21.1 degrees. Uh-oh, we got a problem, right? Because if we fire 21.1 degrees, that's not in the range of the mortar. The mortar cannot fire anything at 21.1 because the range for the mortar is between 45 and 85. How we solve this? Oh, just a second. We can have the same range for the complementary of 21.1, right? How much is the complementary of 21.1? That finally is going to be the angle theta that I'm going to fire with the mortar. So the angle theta that I'm looking for is 90 minus 21.1. And this is what? This is 90 minus that. So it's 68.9 degrees. 68.9 degrees. Look at that. Firing 21.1 that I got here is not good, right? Because I got, in reality, I got here the sine alpha equal this. I need to divide it by 2. I'm saying that the angle theta that I'm going to have for here, if I consider this alpha, I have this angle, I'm going to have 42.2 divided by 2, 21.1 degrees, okay? So that's the first solution that I got for this, 21.1 degrees. The mortar cannot do that, but if I think about the complementary angle to have the same range, is 68.9, and 68.9 is in the range of the set of the mortar. So I can set the mortar to 68.9 degrees. Right? So we already got that this angle theta, 68.9 degrees, is gonna take the, is gonna pass the mountain. Oh, but there is one more problem here, guys. The mountain is 850 meters high. Oh. Okay. So this height is 850. So once that I got this angle now, I need to know if the maximum height is above the mountain. Because the mountain is 850 meters high. I forgot to tell you that the mountain is 850 meters high. I don't have that guy there. He moved up 800 meters to be there. He spent 1 hour to get there. Okay, so at this angle, firing at this speed, I got the maximum height above 850. That's the next question that we need to answer, right? So here's the point that I got the angle finally, but we know the height of the mountain, and we need to check if the maximum height here, the delta y max, is above 850 meters. So that's not difficult to calculate, right? So I know the angle, I know the initial velocity, right? The projectile is going to be launched at 162 meters per second. I already know that this angle is possible to get P, 68.9 degrees, right? So now I need to check the delta y max to see if this thing is going to pass above the mountain, which is 850 meters high, right? So the delta y max, you remember, we have an equation for that, right? The delta y max. The delta y max is V initial squared sine squared theta, V initial squared sine squared theta over 2g, right? So I have the angle theta 68.9 degrees. The V initial is 162 meters per second, right? G is 9.8. Doing this calculation here, take the square of this, divided by this. The delta y max that I got, okay, doing that calculation for 68.9 degrees is 1,165 meters. 1,165 meters. Oh, that's great. It passed the mountain. The mountain is 850, right? So this is 300 meters above the mountain, right? So that's the maximum height. right? 300 meters above the mountain. So no problem with that, okay? So even knowing that the mountain is 850, my condition until now tells me that I can get to the point P, right? With that angle being launched at that speed. So what's the next thing that we need to calculate? Is exactly how long it's going to take for the projectile to get there. You remember, that is going to be the next move for us, is to calculate how much is the time of flight. Because knowing how long it's going to take there, I can have an idea how long is the same time that the tank is going to be traveling this distance d. Right? It's the same time of flight. So the time of flight is what? It's 2 v initial sine theta over g. So I know the v initial, 162 meters per second. I know the angle, 68.9 degrees. We already know that is fine. The mortar can fire that angle, is above the mountain. Doing this calculation here, I got 30.8 seconds. 30.8 seconds, almost 31 seconds for this projectile being launched and get to P. So it means that this distance here, the tank moving 30 kilometers per hour, it's going to take 31 seconds to get there. So where is the tank for that 30.8 seconds? So we know that speed is distance over time, right? The distance d is going to be the speed of the tank, that we are called just Vt, the velocity of the tank, multiplied by time, right? So how much is the velocity of the tank? I cannot use kilometers per hour, right? So I need to write this in meters per second because I'm going to enter here with the time in seconds, right? So this is what? 30 kilometers per hour is 30,000 meters per 3,600 seconds. So this is 30 kilometers per hour. The kilo is 1,000, so it's 30,000 meters by 3,600 seconds, right? So that is the 30 kilometers per hour. Multiply by 30.8 seconds, I'm going to have what is the distance where the tank needs to be. This guy B is going to tell the guy A exactly when the tank got to that distance. He has this apparatus here that he can look distance horizontally and estimate that distance, right? So he's going to tell what distance is that. So that distance, and this guy is calculating everything, right? He's going to say, when it gets to that distance, you tell him that I'm going to fire the mortar, right? So doing this calculation here, that distance is 257 meters. So if the tank got 257 meters from the point P, if it continues moving 30 kilometers per hour, it's going to take some time to get here. It's going to be exactly the same time that the ammunition of the mortar are get to P and get the tank. Right? You can say, well, it looks nice, right? The guy doesn't do that anymore, right? They do. This is what they do. This is what they do. Obvious that we don't have a guy there with with a calculator. They have a lot of tables. Sometimes today they have iPads with tables and distance for the kind of ammunition that you have. What's the angle? What's the distance? So some guy just using GPS tells what the distance is, and this guy here look at the table, know what's the angle of the mortar to get at that distance, right? And eventually you have much more sophisticated kind of ammunitions and other kinds of guns today that can use GPS, that can track towards the tank by infrared, because the tank is hot a lot, right? It emits a lot of infrared. So eventually you can have some kind of ammunition that is going to be guided to the tank through infrared. There are some crazy stuff now that they just put on the shoulder of a soldier, right? It's some kind of a guided missile being guided by optical fibers, right? So when the rocket flies, it left behind an optical fiber, and then a guy here in the control with a joystick is going to exactly take the ammunition to the tank, right? It's called a fog missile, right? So the fiber optic guided missile, right? So this is something from my time when they start to develop this. I worked with optical fibers so many years in mechanical properties, and I remember this. So that was the project, to use fiber optic guided missile to catch tanks behind a mountain. Right? So today there are much more sophisticated kinds of guns, but just using projectile, and that's a good illustration how it's possible to use projectile motion to solve this kind of a problem. I see you guys next class. Bye-bye.